The purpose of this lab was to observe the motion of some object that is moving at the same speed without changing direction. I chose to roll a basketball in the same direction at the same speed. Using Newton's second law in Python, I modeled the basketball's motion. And Newton's second law was used because it can predict the final velocity and position of an object using initial conditions that I will describe later. By graphically comparing the experimental and modeled positions of the ball, I justified that Newton's second law could be used to effectively predict motion to a certain extent. So now let me describe the experimental setup to you guys. In order to analyze the motion of the basketball, I used Tracker. I began analyzing by specifying a video frame in which velocity was constant, depicted by these black arrows here. Next, I used a calibration stick to span the ball's 0.22 meter diameter and place the ball's center of mass at the origin of my axes with the plus x direction in the conventional right direction, right here. Because I was interested in the translation of the ball, I identified the object's position by its center of mass. Tracker then recorded the object's position over time in this chart here. Now let's talk about the model. How did I model this motion? In order to model the basketball's motion, I needed to start with some initial conditions and assumptions. I weighed the ball to get its 0.624 kilogram mass and used the chart and tracker to assign the ball's initial position and velocity. More specifically, initial velocity was found using the first two position and time points and calculating delta x over delta t, because that's equal to velocity. Using a while loop, as you can see here, the ball's velocity and position was calculated after every delta t. So after every delta t that I specifically assigned in my Python program right here, 0.033 seconds. I had to assume the sum of all forces, or F net, was 0 because it was assumed that the ball was moving at a constant velocity. Looking at Newton's second law, we can see that in order for Vf to equal Vi, this portion right here must equal 0. The only way for that to occur is if F net is equal to 0, because the ball's mass and delta t are all greater than 0 or positive. Newton's second law was then used to predict the position of the ball after every delta t. When graphically compared, we see that the model and experimental motion are quite similar but not identical. The model slope is constant and linear because it is assumed that 0 forces are acting on the ball. The experimental motion deviates from the model because in reality the sum of all forces acting on the ball was not 0. Whether this uneven distribution of force was due to friction or other forces, we do not know. All we know is that it is not equal to 0. However, in the model, recall that F net was assumed to be 0. Furthermore, because the center of mass was not known for the entire experiment, incorrect position values may have been recorded, thus causing more deviation from the model. Now I just wanted to touch briefly on the what if question that was proposed here. Using Tracker, we can see that if the axes were flipped, say 180 degrees flipped, the entire graph would also be flipped. So with that being said, the direction of the graph would change, but the magnitude and makeup of the experimental graph would not change. Also, with regard to the what if question, the what does it mean question, I've already discussed that we do not know how many or what exact forces make up the net force acting on the ball. All we know is whether or not the sum of all the pushes and pulls is 0 or non-zero based on the position time graph. Thank you for your time. I really appreciate it. My name is DJ Lewis, and have a good one.